Technology. Yeah, on behalf of Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur, I would like to welcome you all in this, the mega event, the webinar series, the Saturday Manufacturing Talks. Our Center of Excellence in Advanced Manufacturing Technology has been set up in early 2018. It is an industry academia collaborative research platform. So our vision is to inculcate the modern concepts so that we can bring innovation in manufacturing. And this we are, trying to do, forming an ecosystem between the large industries, small industries, academic institutes. And under this Center of Excellence, we are organizing this webinar series, Saturday Manufacturing Talks. We have started our journey on March 13. Our esteemed alumni are working on different aspects of manufacturing across the globe, both in academics and also in industrial practice. So they are delivering lectures on interesting topics, different, the state-of-the-art research taken place in the field of the advanced manufacturing. We have listened to topics on the soft robotics, design of experiment, process modeling, manufacturing, process automation, AI in manufacturing, Industry 4.0, and today we are also, going to listen to one of the important topics, which is the role of AI in manufacturing from Professor Manish Kumar. I'd like to give a brief introduction about Professor Manish Kumar. Professor Kumar has received his Bachelor of Technology degree in Mechanical Engineering from our institute, IIT Kharagpur, in 1998, followed by he has completed his Master's and PhD in Mechanical Engineering from Duke University in the US in 2002 and 2004 respectively. After finishing his PhD, he has worked for postdoctoral research at various institutes for a substantial period of time at Duke University, the US Army Research Office, and also the GRASP Laboratory of University of Pennsylvania. He started his career as a faculty member at the University of Cincinnati in 2007 in the Department of Mechanical and Materials Engineering, where he currently serves as a professor and graduate program director. Professor Kumar's research interests include unmanned aerial vehicles, robotics, decision-making and control in complex systems, AI, multi-sensor data fusion, swarm systems, and multiple robot coordination and control. Professor Kumar is also served as the Associate Editor of ASME Journal of Dynamic Systems, Measurement and Control, and also the ASME Journal of Autonomous Vehicles and Systems. With this brief introduction, I would like to request Professor Manish Kumar to deliver his talk. We are all waiting for this interesting topic. Today, everybody is talking about the AI. So how much role AI has got in the field of the manufacturing, starting from the robotics towards the factory operations and quality inspection. Professor Kumar.
Thank you very much, Professor Paul, for kind introduction. It is my pleasure and a true honor to be giving this talk in front of you all at my alma mater. And can I please share my screen? Yes, thank you.
I think now you can share that.
All right. Can you see my screen now?
I see it has come up. Please go to the presentation. Yeah.
Okay, good. Thank you very much. So before I start, I would like to convey my sympathy and wishes for growing COVID cases in India, and I hope and pray that this wave of COVID subsides soon. Before I start, I would like to give a brief introduction to University of Cincinnati. I'm not sure how many of you are aware of this university. It's that's the place I'm working currently, And what you're seeing over here is the West Campus of University of Cincinnati campus. And so UC, or University of Cincinnati, is a mid to between mid and large scale university in US. It has around 46,000 students. It is among the top tier of the best national universities, as ranked by US News and World Report. It's also classified as R1, which is Research 1 doctoral university with very high research activity. Sorry, it's hold on 1 second. This appears I do not have control over here. Let me see. All right, so so the College of Engineering Applied Science at UC has 6,000 students, and it is well known for, among other features, it's well known for cooperative education. It is ranked number 2, and it's also founder of cooperative education. Cooperative education is a kind of education where students are exposed to practical training via internships as a part of their education program. So the Department of Mechanical and Materials Engineering that I belong to has undergraduate and graduate programs. Among undergraduate program, it has programs in mechanical and mechanical engineering and mechanical engineering technology. And it has graduate programs for mechanical and material science and engineering. And among the research thrust area are included are structural dynamics and acoustics, intelligent prognostics and autonomous systems, advanced manufacturing, simulation applied mechanics, biomedical nanotechnology areas, thermal fluid and enhanced heat transfer, and material science. So this is my brief bio. I will skip this slide because Professor Paul already introduced me. And also before I start, I'll just give a brief introduction to what kind of research I'm currently doing at University of Cincinnati. I am director of Cooperative Distributed Systems Lab and co-director for UAV Master Lab. A lot of my research is currently involving UAVs and robotics. So here we have around a big indoor flight test area with motion tracking system, and we have built several of multi-copter systems and fixed wing systems that we play around with. And among the research areas, we are working on navigation path planning, multi-sensor fusion for situation awareness and tracking of drones. We are also very much interested in novel design of UAVs, the drones, carrying out their system identification and control, developing their control flight controllers. What you see over here is a novel design of quadcopters that allows the rotors to tilt and arms to slide over here. We are also working on large-scale optimization problems with applications in UAV task allocation, as well as UAV routing and path planning problems, specifically for national airspace integration of UAVs. Also interested in indoor UAV applications, and the last topic shown over here, AI for industrial applications. This is something that we'll talk today. This slide shows some of the current and past projects that we have been involved in. What you see here, we are using UAVs for wildfire monitoring and emergency responses. Here you see that video obtained from drone is being processed to obtain traffic parameters, doing traffic monitoring, doing things like finding out speed of the vehicles, traffic count, and various traffic flow parameters such as saturation, flow rate, and all. Here, these pictures that you see is UAV routing problem, particularly for their integration into airspaces, urban airspaces, and how they can work with other UAVs in close proximity. Indoor application of UAVs is another big area we are interested in, and one of the current applications that we are looking at is a telehealth drone. So a drone that can go into people's homes and inside homes and provide telehealth sessions for the patients with doctors, and also deliver medications and retrieve tests from patients. So this is the outline of my presentation today, and I'll briefly talk about AI in manufacturing. We are all quite aware of how AI is impacting manufacturing, but I'll briefly introduce that. And then I will talk about three different test cases of where AI has been used in various manufacturing tasks. One is multi-manipulator cooperative control, so multiple robots carrying a common payload. The second is non-invasive CV, that is a computer vision toolkit that is used for obtaining process parameters in legacy old machines. The third case study is one-shot learning for inspection tasks. So how can we use minimal amount of data for carrying out quality inspections? And then I'll conclude our talk here. The AI, we are seeing increasing role of AI in manufacturing, and I would say that this increasing role has been brought about by technological advancement in allied areas. One of that is computing and processing, and second area is sensing, where we can sense all different kinds of things that we want to sense, obtain data about. And the third area is communication, where data can be sent to anywhere, anytime, with minimal lag in time. Now, in terms of applications of AI in manufacturing, it's been applied in a lot of different areas. So one very primary area is optimized in plant operations, where AI tools can be used to improve the operations of plant, to provide better throughput, overall throughput of the plant. Also at machine level, AI tools can be used to improve the process parameters, to improve quality and production time. One of the other major areas of AI is in diagnostics and prognostics, where data, large amount of data from monitoring of various machines can be used to understand the degradation of machines, and carry out things like predicting remaining useful life, or understand any potential health problems with the machine. And then the third area is that of situational awareness, which basically means that AI tools can be used to obtain data, process data, in order to have an awareness, a picture of the environment, of the complete plant environment. So where are the raw materials, how they are being used, which machines are working and not working, and then this kind of overall situation awareness can be used to make decisions and improve plant operations. So we all know about Industry 4.0, 5.0, which are the concepts which refer to the fourth and fifth industrial revolutions, which are brought about by convergence of several different areas of research and work that include additive manufacturing, AI, big data analytics, simulation and visualization, IoT, cloud computing, cybersecurity, autonomous robotics, augmented and virtual reality, and at the center is also the human technology interaction. So I'll start with my first case study. This is multi-manipulator cooperative control. This is the work that I did as a part of my PhD studies at Duke University. And the problem is over here is this, that now in many of the industrial tasks, manufacturing tasks, you need to manipulate or transport big, bulky objects that cannot be transported or manipulated by a single robot. In that case, you need to make use of multiple robots to carry out the cooperatively transport those big payloads. So in those cases, you need to make sure that that the contact forces, when you try to have multiple independent manipulators working with physical interaction, then the contact forces get built up. You need to keep a check on that so that it does not affect the operation and it does not hurt the robots. So over here, this picture shows the two ABB robots, ABB 6 degree of freedom robots that are used in transporting. There's a common payload over here, and the two robots are trying to carry this payload. Now I'll show you a video which basically shows that how this operation is done. Typically, what is done is the robot's trajectory is kind of pre-planned, and you do an accurate positional control of the robot, so that the relative distance between an orientation of the robot remains fixed, so that the object can be effectively carried by the two. But the problem with this approach is that as you start moving, due to errors such as misalignment of axis and the positional inaccuracies, the contact forces at the point of contact keep building up, forces and moments, and there comes a time where these become too big, so that it triggers the obstacle avoidance, collision avoidance algorithm in these robots. So this is what has happened over here. It stopped operating because of those forces and moments became too big. So which you can also see in these graphs over here, that as forces and moments keep building up as you carry out these tasks. So to alleviate this problem, there are conventional control techniques used in literature, and those techniques like admittance-based control, impedance control, that look into both the position and forces, try to control both of them. If you want to use those techniques, then you need to have access to the complete dynamic parameters of the plant or the system that you want to control, which may not be available in all cases. In this case, we were not given the dynamic parameters of the robot, so we do not know how, it's all inertia and detailed design. So the question becomes that can artificial intelligence, machine learning be used in these circumstances where you can learn some of these parameters, you can develop control where you do not have access to these parameters. So what we proposed was a fuzzy logic-based control, and we all know what fuzzy logic is. It tries to emulate the way human do their inferencing and decision making by using linguistic variables, and how these linguistic variables are related to each other, which is captured in the form of knowledge base or rule base. So the fuzzy logic control was proposed here, and what we did was that we had forces and torque were the input to this controller, and the output of the controller was a compensatory motion. So think of this way, that these controllers were taking the contact forces and moments And as those contact forces and moments were building up, it provides a compensatory motion on the one of the robots, so that the objective of this controller is to minimize that control forces, the contact forces, by providing this compensatory motion. So we use two different approaches. One was the fuzzy logic controller that was developed manually, and that's a popular way of developing fuzzy logic controller because of the way this fuzzy logic controller is designed. It allows incorporation of human intuition and human expertise in the form of membership functions and rule bases. But the problem with this approach is that for complicated systems, it can become very difficult to have that kind of user or human expertise. And also, when humans design fuzzy logic controllers, it's usually not optimal. So another approach traditionally used in literature is that use some of the optimization techniques, like you can use generic algorithm, particle swarm optimization, all kinds of optimization tools to find out those parameters of the controller. Now, to do that, you need to have either a lot of data or you need to have access to the simulation environment. So what we proposed over here, in this case, we did not have either of those. So we proposed a technique called NeuroFuzzy method, which can be implemented in online fashion. So you can have this controller that learned its parameter while the system is in operation. So for the manually tuned fuzzy logic controller, we have two separate, so the controller consists of two separate fuzzy logic controllers, one for each direction in X and Y. So we are looking at the planar motion when the payload is being transported along X and Y. And each of these fuzzy logic controller has two inputs. One is force in that direction, in X or Y direction, and then the torque in Z direction. And output of the controller is movement in millimeters. That's your compensatory motion. So these are the two inputs, now force, torque, and this is the output movement. And these graphs over here show the different membership functions used for this application. And then you have this table that shows the rule base, and rule base is basically manually tuned, manually obtained using intuition and in human expertise. So for example, if you want to introduce compliance in the system, you need to move in the direction of force applied. So you can say that, hey, if the force applied is large, then move by large amount. So using that kind of logic, you can build this rule base here. So the second approach is that of NeuroFuzzy, and in this approach, what we do is that we take the fuzzy logic controller and develop a corresponding neural network of that. So it basically means that fuzzy logic controller, all the mathematical operations that we do in fuzzy logic controller, is represented in the form of operations in a neural network architecture. So for example, over here, all the operations, fuzzy logic operations like fuzzification, defuzzification, and all the rule bases, how they are combined, all that is done in different layers over here. So the first three layers carries out fuzzification. This layer 2 carries out output membership function, and this the computations over here represent all the rule bases, how they are combined. And finally, layers 3 and 4 over here represent the defuzzification process. So why are we doing this? We are converting fuzzy logic into a neural network architecture. And the reason for doing that is that for neural network learning, there are a lot of tools available. There are a lot of progress that has been made, and most popular among that is the backpropagation. So you can use those learning mechanisms like backpropagation once you convert it into a neural network architecture. So the idea is that now this neural network can be used in online fashion. So it applies input to the plant gives output. You use that output via some kind of algorithm to train this network. And remember that this neural network is essentially another representation of the fuzzy logic. So this basically at the core, this is the fuzzy logic controller. Now the main contribution over here is that how do you develop that algorithm that trains the neural network? And over here we propose what is called what it uses model predictive control. So model predictive control is a well-known tool in the field of control theory. Basically what it does is that you use a model, a plant model that can show the output, give you the output based on the input, and you use that model to predict the output for a certain period of time, and you see that whether those output matches with your desired output or not. So you can construct an optimization function, objective function, like what is shown here at the bottom, that shows that of how if the output matches the desired output for a certain period of time, and that period of time is called horizon. Then the objective is to find the best control input that will minimize this kind of objective. So we used something similar to that here, and the overall architecture of this neurofuzzy scheme is shown here. So you got over here two controllers, neurofuzzy controllers in long X direction and long Y direction, and the output of that is your compensatory motion, which is fed to the plant, and this is also fed to these two neural network model. These are the plant model that are used for prediction purposes, and these are also being trained in online fashion. So output of this plant is compared with the output of the neural network models over here, and that signal, the difference, is taken as a backpropagation signal to train these networks. Now there are two other blocks over here. One is these are the optimization algorithms. So these are the ones that are implementing that model predictive control optimization. So what they are doing is that they're saying that, okay, if I use these controllers and use this model to predict, is it giving me good results? If it is not giving me good results, then how can I use this model to better these networks? So that part is also done by backpropagation algorithm. So essentially, we have these two blocks, which are the neural network plant model. These take input as moment, movement, and the forces before the compensation is provided, and it predicts what will be the forces and moments, contact forces and moments, torques after the application of force, this compensation motion. And you have it for both X and Y direction. And similarly, these optimization algorithms over here, they are trying to minimize the contact forces at those points of contact. So that's the objective function is shown over here, which is the sum of square of forces and torque. So these are some of the results over here. This show the control surfaces for the manually tuned. This is the manually tuned fuzzy logic controller, and this is what has been obtained after tuning through this online learning process, the AI-based learning process. And these are some of the results obtained. What you can see over here is that you can see that when compensation motion is provided, there's a sharp decrease. The sharp decrease that you see is after the compensation motion is provided in X and Y direction. And this is for the manually tuned fuzzy logic controller. This is for the neurofuzzy controller. And what's shown over here is the results that show the reduction in these forces and moments, combined forces and moments after application of compensation motion. So you can see that the fuzzy logic controller reduced by 77%, the neurofuzzy reduced by 79%, a slight increase. But what is important over here is that these neurofuzzy controllers were able to learn the entire thing from scratch by itself from data. So you're doing this in online fashion, and you are learning it in an online fashion from scratch. You are not using any of the pre-tuned values. So to summarize this case study over here, we are using a tool, neural network, AI-based tool, neural network to obtain or train the fuzzy logic controller in online fashion, and we show that this works pretty well for a complicated task like robots cooperative transportation. Now, this is work that I did as part of PhD, which was like 15, 17 years ago. We have a similar problem here in the drone. So now I work more in the area of drone. And the problem of cooperative transportation is also there in drones. And people are trying to see if multiple drones can be used for transportation. And now that has several advantages as compared to designing a single bigger drone that can carry bigger objects. Using multiple smaller drones has several advantages. So, but this problem of cooperative transportation in drones is a whole lot more complicated than for mobile or for fixed manipulator robots. The reason being that drones dynamics is inherently very unstable, and the fact that if it doesn't work, then the whole thing comes crashing down. So that's one problem. The second problem is that when we're using drones outdoor environment, it is very, very hard to get very accurate positional feedback, because outdoor you are using GPS, which is a preferred way of obtaining positional feedback. GPS itself has a lot of errors which are of the magnitude of meters. And with that kind of error, you cannot do a pure position controller based scheme. So what we proposed was similar to what we saw earlier, force-based feedback in the leader-follower framework. So over here, the idea is that you got one drone which acts as a leader, and that over there you are implementing a position controller so that it follows a trajectory to go to its final destination. The other drone is a follower drone. Now, what it does is that it monitors the forces and moments that are acting at the point of contact and uses that information to comply to the motion. Just follow the motion of the leader robot and leader drone. So this is the control architecture shown over here. This is the one in the top over here in blue is for the leader drone, and this at the bottom here is for the follower drone. And there's some nice, interesting experiments that we did with this and simulation studies. So this over here, you see that another very nice application came where we are using a human-drone interaction using similar techniques. So human is providing cues and controlling the drone by moving the stick around. So this is an example of human drone. So you can use either stick or tether to control the drone. Now, if you come to the second case study, which is the computer vision toolkit for non-invasive monitoring of factory floor artifacts. Here, the problem is this, that this is part of a project that we did for DMDII, which is a consortium here in US of industry, and so the member industry came with a big problem that they face when their factory flow plants have both older machines and newer machines. So the older machines were not digitized. They have analog devices, all these cases and everything. That's how you monitor the older machines. The newer machines have everything digitized. So all these data can be fed to a central monitoring unit directly. So you can be in front of the computer and can see how all machines are working. Now, older machines for older machines, they need to go manually and monitor all these parameters. So that's a big problem, very manual, very time consuming process. So the objective was to develop some innovative, affordable, and non-invasive toolkit that can acquire data from all these old legacy machines and send the data to the central monitoring unit and seamlessly integrate the data using what is called MT Connect. You probably might have heard of this. This is an industry standard for communication of data in manufacturing industry. So this shows the flow of what we have. We got legacy machines. These are the old machines that are not digitized. These are the new machines, and this is our proposed system. So what this system does is that it looks at this machine, whatever parameters need to be monitored, it is seeing that using camera. So camera monitors the machine and uses computer vision and sends the information back to the central monitoring unit, which can be software like SoftFloor IQ or SCADA systems. So this shows our solution to this. This is our solution has a camera, so it's a standalone of the solution. So it's a complete toolkit which you can just put it at any machine and start recording data, send the data to your central units. The idea is that there's a camera that will be looking at what you want to monitor. Is it gauge? Is it a LCD panel? And it will read those data and digitize it using computer vision tools, and then send it to the central monitoring unit using the MT Connect adapter and agent. So those are the MT Connect applications. So here is a camera, and this is the main unit, the processing unit. This is a computer on which we are running Linux Ubuntu and running all different kinds of computer vision software. And this slide shows the different kinds of components that we looked at. What you see over here, the fixture, the orientation of fixture is very important while doing operations using fixture. You see over here is the LCD panel that is used, safety lights. We have 7-segment display. So this is, we are reading this using camera and sending that information. We're also finding out position of the switches, on or off, analog devices, analog gauges like this over here. And this shows a typical panel that the camera will be looking at, and we'll be telling everything over here, like what is the position of this switch, what is the reading, is this light on, what is the reading over here, what is being displayed over here. All these things can be acquired using the camera and sent to the central monitoring unit. This shows, there are all different kinds of things that we are doing over there. We are doing optical character recognition. We are doing finding out positions of the needles. All these things require different kinds of image processing tools. So this just shows a particular one particular tool that we are using for optical character recognition. And this shows the series of image processing that is done in order to do that. So you convert into grayscale, carry out denoising and deblurring, and then you do the image obtain the binary image, and then carry out segmentation and do the character recognition. So likewise, there is a process flow for doing all different tasks that we identified, like switches and gauges and other things. Other thing that you can appreciate over here, that you got one camera and looking at so many different panels, it is difficult to position the camera. So, but then you have, like over here, you will not have a perpendicular position for looking at this piece of object. But then you can use image processing tools to transform that image so that you get a better perspective of this object. And now this shows, this is a mock panel that we developed at University of Cincinnati with all different kinds of things you see. This is a LCD panel. These are the gauges, different kinds of gauges that you see, lights, switches, all different kinds of things. And you see that this camera is looking at it, and it's reading all of them. One camera can do everything over here. You can read all of these, and the output is displayed over here in red, what you see over here. So likewise here in here you're seeing that it is reading this panel, LCD panel here, and transmitting the data to this SoftFloor IQ. This is your SoftFloor IQ software. And likewise, this is for the fixture orientation. So these fixtures need to be oriented in certain fashion. If they are not oriented, it sends out a fault signal. So that can be visualized using the SoftFloor IQ. This is our mock panel here. And what you see over here is the digital twin of this mock panel. So everything that you have over here is digitized here, right here. So all, and you can, you have a camera that looks at this and gives all the information in real time, which is displayed here in the digital version of this mock panel. So essentially what to conclude for this case study, what we had was a very, very genuine problem that industry faces, and how these AI tools can be used to solve that problem. It's a pretty low cost. You got one camera, the camera's costs are very low, and you got one computer attached to it, and that's it. It's not invasive. You do not have to open anything there. And then this kind of approach lets you digitize these old legacy machines. These are machines which cost millions of dollars, and industry cannot just get rid of them, but they still need to keep monitoring them. So this kind of tools, you can see that how AI can help solve these types of problems. So this is the last case study, and this case study is one-shot recognition of manufacturing defects in steel surfaces. We all know the manufacturing, the inspection process is so important in manufacturing. It's one of the tasks in manufacturing, and manual inspection is a very popular way of doing that. But manual inspection is a pretty monotonous job, very prone to manual errors. Now, AI-based or automated inspection is also very popular, and as you can see over here, that AI-based technology can help here. Now, if we are talking about cameras, images used for inspection, then one of the most popular tool that has come out recently is that of the deep neural networks. So you all probably are aware of this. So deep neural networks are basically the neural networks which have deep architecture, and the advancement in last 10, 12 years have resulted in using these deep neural networks for carrying out a lot of pattern recognition and classification tasks, and it's been very successful. And you can see that it's been used for a lot of purposes. You see this over here. It's used for PCB, printed circuit board, and finding out defects in gearboxes. So it's pretty popular. But the problem in using deep neural networks is that it requires large amount of data. I'll show you a typical deep neural network. A very popular one is convolutional neural network. that is used in image processing a whole lot. And a simple CNN, which its architecture is shown over here. A simple CNN, which is processing, let's say, 200 by 200 images by pixel images, can have millions of parameters that need to be optimized. Now, how would you optimize those parameters? You do the learning using the backpropagation method, and but to do that, you need a large amount of data. Tens of thousands of images for each classes to be trained. So now obtaining data may not be that problem for many applications, but you need to do the annotations there. That's a manual process. You need to label the data, and there's a whole lot of industry, as shown here, developed because of that. You have the data annotation is an industry in itself. So that's one problem. It's very manual, very expensive work. The second is that in many of the tasks that you do not have access to that data, like failure. If you are doing failure analysis, you do not have a lot of failure data. In many applications, things don't fail as often, so you don't have that kind of data to train, and this is a big problem in certain applications. So what we are proposing over here is what is called one-shot recognition. It basically aims to learn information about object classes from one or at maximum a few training images. The goals of this algorithm is that it should have good generalization capability to new examples, new classes. It should have good transferability from different concepts, you can transfer knowledge from one application to the other, and the high classification accuracy with limited data. So this is what we have proposed over here. It's called Siamese neural network. Essentially, what it has, so the basic concept behind this is this: that for classification, if you want to do classification like using let's say CNN, then you need a lot of data because you need to get information on each classes. Now, what the Siamese network does is that it does not do the classification that way. It says that, okay, can I use two images and say whether the two images are similar or not? And that way you can do classification. So it basically has two identical networks. So over here, one network is there, and the second network is over here. And there are two images which are set as the input. And what it does is it does all the processing over here. At the end, you have a feature vector that comes out, and you find out the distance, the Euclidean distance between these two feature vectors that can be used to say that whether the two images, x1 and x2, two input images, are from the same class or not. Now you can see that this can be used in classification. If I know one class of one image, I can find out whether this image belongs to this class or not. So that's the main idea. Now, for the training purposes, you use what is called contrastive loss function. It's a specially designed loss function that says that if the two are from the same classes, you're using the Euclidean distance between these feature vectors as the loss. If they belong to the different loss function, different classes, then you penalize it by introducing this this cost in the loss function. Now, we used Northeastern University data for identification of steel defects in steel surfaces, and there are 6 different defects that we are trying to recognize. And the data is very limited. It has only 300 data sets for each classes of defect. So we augmented that data using affine transformation and some randomization to obtain 900 samples of each type of classes. And so this is the result that is coming from the training. This is the training and validation loss that you see as the number of epochs. But what is very interesting is the results shown over here. So what you see over here is that one is that the k nearest neighbor based technique does not work at all. in this scenario. The Siamese neural network gives 83% and the CNN gives 93%. Now, this is not bad, because what Siamese neural network did was it used only 3 classes out of 6 classes. It used data from only 3 classes to for the training purposes, while testing was done in all the 6 classes. Now, this is something that CNN cannot do. CNN needs data from all the different classes to be trained. And 83% accuracy is not bad if you consider the fact that you were not even introduced to those new defects. Now, we also checked that, hey, if we give all the data to the Siamese neural network, how much will be the accuracy, and as compared to the CNN. So we did that over here, and now we see that the accuracy is pretty comparable. So to conclude this case study, we used one-shot learning using Siamese convolutional neural network for identifying defects in steel surfaces. Now, this method is the image processing based method, so it's very non-invasive as compared to other destructive testing that is done. The other advantage is that it requires minimal amount of label data. So that's the one big advantage, because some failure data are very hard to obtain. The future directions over here, we used very generic architecture. We can optimize the Siamese neural networks architecture. We can use transfer learning to improve the accuracy. Also use multimodal data. Say, for example, we are using just vision data. We can also use things like multispectral cameras and all to improve accuracy. Also, I'd like to mention over here that though we are using the images over here for these purposes, and but these tools, CNN and Siamese neural network, can be used to also identify defects using time series data, or identify health of a machine component using time series data. So with this, I would like to acknowledge my collaborators and students. Dr. Dave Garg, he is my advisor for PhD. Dr. Anand and Minay, they are my collaborators here at University of Cincinnati. David, he is our industrial collaborator, and the students, Shraddha, Aditya has been working on both the one-shot recognition and CV toolkit, and Anil and Vinay, they worked on the CV toolkit. And I would like to acknowledge support from funding agencies who have supported the work, my lab. So with this, I will end my talk here. I hope I finished it in time. And I would like to invite questions and have discussions.
Yeah. So, Professor Kumari, they finished exactly on the time. So thank you so much. It was a wonderful lecture. I was just wondering when I listened to your talk, the 15, 16 years back, whatever you have done on the real-time neurophysics control for the multi-manipulators, it's still very much applicable in today's, the automation perspective. And you've rightly seen that, the multi-tone, the aspects for while handling the material, how much difficult it is, because the situation is very much the unstable dynamic. So, we are busy with that. And I like the concept of, the computer vision systems by using the MT Connect, so that the real-time data you can acquire from the legacy machines, which is very, very useful for my understanding for the MSMEs or the SMEs, because they would like to adopt the Industry 4.0 concept, or the implement the digital tools to get to know about the health of the machines. So they can't, rightly told that they can't replace the old machines. It's not possible, specifically for the MSMEs. But at the same time, they would like to know how they can optimize the operations. So it's a very wonderful application.
Thank you, Dr.
That's a
Pal.
very good. Yeah, so I am requesting the audience to, the very interesting talk. So definitely there will be some questions. I'm requesting the audience to send us the questions. They can write it in the chat box or they can unmute and place the question. Question, please. Before audience asks the questions, I am having one more question in my mind. I'd like to ask you. You have mentioned about the the Siamese network and then CNN network, and then you have given very nice comparisons regarding this performance. When large number of data is there, they are performing almost the same. So can you just give us some idea about the real-time applications by using the Siamese network?
Right. So the application, what we were motivated over here was this, that there's so many different applications where you do not have access to data. If you're talking about, say, for example, you're monitoring process parameters and seeing whether a nuclear facility fails or not. I'm just giving an example. How many times a nuclear facility would fail? You do not have that kind of data. In many of the tasks, you do not have data of the failure data. So what can you do? How can you train the network? The CNN has been used a lot for identification classification problems, but they require a lot of data to train. That's one of their major drawbacks, and they're being used in almost real-time applications. So that's depending on now with use of computing like GPUs, you can accelerate the processing a lot, and a lot of these neural networks can be very easily their computations can be parallelized, so that they can do parallel computing using GPUs. So there's a lot of real-time applications that are happening of these networks. But problem that we're looking at is that what happens when you do not have as much data? How can we still use these deep neural networks? Can there be new novel architectures that we can develop where we can use these networks for classification in cases of less data?
Yeah. So there are some questions.
Questions
for you.
Yeah, thank you very much for your nice presentation, sir. I was just wondering, I like your entire presentation, that particularly the third piece, where you talked about that one-shot inspection, that part, wherein it can have a very good impact in future smart manufacturing process. We can, shorten our inspection time. But one thing I was just thinking that how many number of sample data is required, because so far when we are generating the number of inspection, we require large number of data. Otherwise, it will not fit the model, and we cannot meet the exact what exactly required. Because it requires large amount of data is required. So when we are going for the large amount of data manually by inspection, it becomes practically impossible. So with a limited number of data, how it is possible to get that level of accuracy?
Right. So that's the key question here. That's most of the methods, like what we talk about CNN, you need a lot of data points for each class. So what Siamese does, the proposed method that we talk about over here, it works in a different way. What it does is that it does not classify. You do not give one input and say that, hey, whether this belongs to this class or this class or this class. Which is typically done by CNN, right? So you give So you show the image, and then it will tell you that whether this is a car, this is a bike, this is a human or what. So it does that kind of classification. What SAMIS does is that it compares two images and tell you whether the two images, the objects that you're seeing in the two images, belong to the same class or not. So this uses the disparity, the difference between the two. It's using that distance metric. It does that. So over here, all it does is that, hey, it belongs to this class. This image belongs to this class or not. Now, by doing that, what is actually happening is that if you have just one image of a new class of defect that you have, so just a new class, you do not have many images of that, just one image, then you can, this method can tell you the test images that you have, whether that belong to this new class or not. And because that SAMIS network is trained on a bunch of data which sees that what are the important features in recognition, for this kind of application. So it already knows that these are the important features, and then when it sees a new one, it matches those features between the two images to see whether there are similarities or not. So technically it needs only one data point for the new class. So that's why it's called one-shot recognition. But with one data, how much accuracy will you get? You will not get as much. If you already train with at least few of the data images, then you will get better accuracy. Does that answer your question?
There are some other questions I'd like to read it. What is MT Connect? Is it a standard software available? This is a question from Dr. Vasu.
So I don't know whether this is an open source, but this is this is a popular data standard for communication. So in industry, you have all different machines, right? A machine manufactured by one company or other companies, and they are using their own data standards. So their way of representing data would be their own way of doing it. Now, MT Connect kind of uses its own method to convert all those data into same data standard, so that you can represent the data on a central monitoring unit. So MT Connect is a communication standard. So I don't think it's available as open source. I'm not sure about that. But if you do a Google search, you will see what this MT Connect is.
There is another question from Professor Nikhil Chopra. So he has mentioned that given the specific application of steel defects, how much data you think on average is required for steel defect applications for sufficient generalization?
So how much? So this is a nice trade-off. So I will not give a number, because there's by giving, it's a trade-off between how much accuracy you want and how much data you have. Having more data certainly will increase the accuracy, as you saw that in cases where we had only 300 data points. So we had only 300 data points, and if we use all of them, then we are getting like 93% accuracy. But if we are using half of it, using only 3 classes, half of it, we are getting 83% accuracy. Now this number may change from one application to the other, but this is a trend that I wanted to emphasize, that you can develop newer means of a different way of doing classification that would require lesser amount of data. As I said, technically, one-shot learning requires only one data point to give you results.
Yeah. Another question is from Mr. Venkata Sai Kumar Reddy. So he has asked that, are there any techniques to solve class imbalance caused by lack of failure data so that model is not biased?
Right. There are a lot of methods to solve class imbalances. So what one is transfer learning. There are a lot of new techniques are coming to solve the problem of class imbalance. You impute data, you introduce augment data, data augmentation, also transfer learning. Those are some of the techniques that people use in solving the class imbalance problem. But again, the technique that I mentioned over here, that's another method of doing the same thing, because over here we're talking about the same problem. We train the data on only 3, and the other classes were not even available, and still you're able to carry out classification pretty accurately.
Question raised by Professor Alok Kanti Dev of IIT Kanpur. He has mentioned that multi-UAV application, though the problem is challenging, given the stability of the UAVs, how to augment its reliability?
It's a difficult problem. UAVs are a whole lot difficult problem. If you have tried to fly a UAV, it takes a lot of tuning. Even if you take things out from build it from and try to write your flight controller, it takes a lot of tuning, and that is because it is very sensitive to the inputs, and so if you design something for one UAV, and your mass changes, you move your electronics to a little bit from the center, again you have to retune it. So I agree that this is a problem in UAVs. That but now how can you get rid of these types of problems? And people are working towards how can we use, say, for example, the concepts from adaptive control, where you can adapt you can take care of the parametric uncertainty, as well as you can take care of the control, adapt your controllers so as to reflect the changing conditions. In many cases, the conditions could be changing, or reflect the uncertainty or lack of accurate model that to begin with. So adaptive control and this we are also working towards using newer deep learning based methods. So deep learning based methods over here, you can think of this way, that you train it using simulations or to have a basic functioning controller, and then you use some kind of transfer learning capability in order to modify it while you are actually using it. You need to have some kind of adaptive ability in order to take care of changing conditions, and I think that's how you can improve the reliability of these systems.
Yeah. So the next question is from Mr. Subir Sirsagar. So based on your collaborative transportations by using the drones, so he has asked, like, how frequently is the mission of the follower drone modified by the force or impact? What is the impact?
So I did not talk in more detail about the UAV drone part. But what drone one is doing is this, that you got multiple UAVs that are trying to transport one load, one cooperatively one payload, and you know where to go. So you have the goal location, and you probably know how the trajectory to follow. So what we are doing is that one of the UAV is the leader. So we call it a leader, and its task is to implement a position controller. So it will give a cue. Its task is to give a cue that, hey, I want to move in that direction. So suppose it's carrying a common payload, and one UAV starts moving in certain direction, and others, what their job is to keep monitoring the contact forces and moments acting on it. And it sees that, hey, one is trying to move in this direction, so there will be a change in the contact forces and moments. And by properly processing that, it will be able to figure out that, hey, I need to move in certain direction based on that. And that is what this controller, the follower controller, uses these input as contact forces in the moments, and it tries to move in a direction which is same as the leader direction. So it is so think of the follower as a fully compliant motion. So it's always, it is, there's no mission for the follower. It's just is complying to the leader's motion. So it is, in other words, it's always complying. It is always following the leader.
Next question is from Mr. Nilesh Kumar. I think it is based on your work on the NP-Connect computer vision. So he asked, like, how can you get rid of the manual interference while capturing the image by using the camera and while using the NP-Connect transmitter? How to avoid the blockage while capturing the image?
So the blockage, I understand the blockage means that you have occlusion that is coming from placing something else. So you got a camera and you occlude, and in that case, the camera is not able to see and read gauges. So in that case, there will be no data. So if you are putting a occlusion there, the camera has no sight of. And this, I understand this is a valid problem, because the camera, these machines are being monitored while other people are working around it. So people can come in front of the camera and they can carry out the occlusion. So what we could do in those cases is that once occlusion happens, there is no reading. You can send in some kind of alert that, hey, this camera is not getting any reading, and probably alert the user of removing the occlusion. But apart from that, if the occlusion is happening due to something which is happening regularly, so the idea is that first put the camera at a place where you minimize this kind of occlusions from other disturbances from others working in that area. Second, if that happens, then you can certainly send an alert, and I think that's the best you can do.
I think the last question is one of the staff members of our group, and he has asked, what is the processing time of fixture orientation detection by getting the coordinates from the controller screen? So how much time does it take to detect the orientation of the fixture from the controller screen while taking the image from the controller screen?
So for that, the application we are talking about over here is the LCD. We have a camera that reads the characters in the LCD, and this is happening in real time. And for this, this process happens in real time, as in we are not having any delay brought about by computation over here. So we are processing data as fast as we are getting it, like 30 frames per second. We are processing data. Also remember that the camera gives us one image, and in that image we have several different things, right? One part is your LCD, another part is your analog gauges. So what we do is that we define our region of interest. So that region, so we say that, okay, over here, look for apply the OCR algorithms to get what is being read over here. So we do that reason of, since the camera position and your panel does not change, so we know exactly where to read. And so we are not processing data from the rest of it, just processing from that particular part. And that process is pretty fast. It's it is almost real time. As you can also see it from the video there, that it not only processes the data in real time, it also sends the data through MT-Connect to that shop floor IQ, where it is displayed in real time.
I think there is no other questions. Any question? Last one or two questions? I think there is no other question. Yeah. Thank you so much, Professor Kumar. It was really a wonderful talk, and we are working in this, the robot to robot control, robot to human control, and all. But I must appreciate that the level and depth of your research work is really fabulous. It's wonderful. Audience might have got a lot of the takeaway from your lecture. I must appreciate, and I'm really grateful for your presence and the lecture. The next week, at the same time, 8:30 p.m. Indian Standard Time, we listening to another interesting talk that is on the Industry 4.0 by Professor Subhadas. So it is on the field, on the mechatronics under Industry 4.0 and how much it has got impact in the education. That's on the 1st of May. Then May 8th, now we'll have the lecture from Professor Kailash Kapoor of University of Washington. That is on the quality control in manufacturing, past, present, and future. And the 3rd week of May would be a lecture, Why Robotics to Robotics. So again, almost this line, we'll listen to Professor Sudhir Kumar Saha. The next, the May 3rd. There will be more. May also the other lectures are there. Lectures are there. Yeah. So that will be on we are here in manufacturing by Mr. Suresh Adina. The May 29 will be the robotic machining by Professor Shreyas Venkotu of the Institute. These are the series of lectures, webinars that we have scheduled till May. And we will be also following this every Saturday 8:30 p.m. for the next the months. Like go as far as possible. Thank you so much. Thank all of you for your